Okay, going to be working on 2.2, separable variables. So number one, we have dy dx equals sine 5x. So what we'll do now is we'll just multiply both sides by dx, and then we're going to do integration on both sides. So we're integrating 1 dy, and we're integrating sine 5x dx. So on the left side you just get y, because we're integrating the constant 1 function with respect to y, so we just get y. And of course we get a constant, but we're only going to worry about our constant on the other side. So let's go ahead and integrate sine of 5x. The antiderivative of that is negative 1/5 cosine of 5x, and then plus some constant, I'll call it c1. And that is it. So that is our function that satisfies that differential equation. So remember, what that's saying is if we take this and we plug this in, we take its derivative, right? If we get dy dx, take that derivative and then take that and plug it in here, then this equation will be true. All right, let's look at number 2. dy dx is equal to x plus 1 quantity squared. Again, rewriting this, multiplying both sides by dx. Now integration on both sides, and we get y again equals, now the antiderivative of this, it's a little bit of chain rule involved there. You could do a substitution for this, but trusting that you're all comfortable with that idea, that the antiderivative of that would be 1/3 the quantity x plus 1 cubed, then plus some constant of integration. So there's our function y. Okay, number 3. dx plus e raised to the 3x y, dy equals 0. Alright, so what I'm going to do here, I need to get all my functions of x to one side and everything that's not a function of x to the other side. So let me take that dx to the other side. It's just going to make it negative. And then let me divide through by e to the 3x. And so what we get is dy on the left equals, let me write it this way, negative e to the negative 3x. So that would have the effect of bringing this up out of the denominator, but I have to write it as a negative exponent. So there we go. We've got all our y stuff on one side, all our x stuff on the other, and now we're going to integrate. So the antiderivative on the left side is y. Then over here on the right side, let's see here, let's just bring that negative out. And then we would have to do maybe a little basic u substitution here. We should get a negative, and then let's see, 1/3 e to the negative 3x, and this has to be negative also, and this is what y equals. So let's just check this. 1/3 e to the negative 3x. If we take the derivative of this, plus constant, I'll put plus c1, plus c1. If we took derivative of this, right, it'd be 1/3, and then derivative of e to anything is itself, then times the derivative of what's up there, negative 3. This 3 and 3 will cancel, we'll still have a negative there, and that will match up with this thing right here. So we're good. That's our antiderivative. So that looks like the function right here. Okay, moving along to number 4. dx minus x squared dy equals 0. And same story, I'm going to move things around. This time I'm going to take the x squared dy to the other side. And then I'm going to divide through by x squared. When I do that, I'm going to get x to the negative 2 dx equals dy. So I divided here x squared, divided here x squared, and then brought that up with a negative exponent. And now I'm going to integrate, and let's see, I should get negative x to negative 1 plus some constant, and then equals y. So that's just power rule on that. And we can just leave it like that. I think that'll work. So that is the function that satisfies that differential equation. Try and squeeze number 5 over here. X plus 1 dy dx equals x plus 6. And so now we have dy dx equals, I have to divide both sides by x plus 1. So x plus 6 over x plus 1. And now we're going to integrate both sides. And hold on, where's my, I forgot, when I divided through by the x plus 1, I multiplied both sides by dx also. Okay? So that's why I have dx here like that. Okay, so let me clear that out of there. Okay, so now integrating the left side is fine, we get y. On the right though, we'd figure out how we're going to do that. So here's what I'd recommend. Just do a real quick little long division. So x goes into x one time, so we get 1 here, gives us x plus 1. We subtract, which changes the signs, and we should get a 5 here. So we're going to have plus a remainder of 5 over x plus 1. So I'm really trying to integrate 1 plus 5 over x plus 1 dx. And I can do those separately. The antiderivative of 1 with respect to x is x. And I have plus, the 5 is just a constant, comes for the ride, and then you should know by recognition that the antiderivative of 1 over x plus 1 is natural log of x plus 1. So that looks like we can just slap that in here. Plus some constant. And we should be good to go. Oh, that was number 5. I was looking at the wrong thing. Okay, yep, we're good. Now, okay, going to be continuing here, number 6. All right, so number 6, we have e to the x, dy dx equals 2x. Okay, so we will, excuse me, we will separate these so we can get everything that is a function of y on the left side and everything is a function of x on the right side. So I'm going to multiply by dx and divide by e to the x. Now we have separated these. On the right hand side, I'm going to do one more thing. I'm going to go ahead and bring that e to the x up to the top and make it e to the negative x. And now I'm ready to integrate both sides. Now on the right side, well, the left side's easy, okay. Now on the right hand side, we've got to do some integration by parts. So hopefully you recognize this from Calculus 2. We're going to do integration by parts. So the way that I do this is I make a table. I write u equals something and dv equals something. I have to pick which of those is which. And I'm using the formula for integration by parts that the integral of u times dv is equal to u times v minus the integral of v times du. So we need to pick one of these to be u, right? And the one that I'm going to pick is the 2x. So the reason I'm doing that is because in the new integral, I'm going to be using the derivative of that, and the derivative of 2x is just 2. So du here will be actually 2 dx. And then for dv, I have to choose the e to the negative x. I have no choice. Dx, and that works out good because I'm actually picking that whole thing there. So this was u and this was our dv. And now to get to v, I have to integrate to come up. So it's differentiation going down and integration coming up. The antiderivative of e to the negative x is just negative e to the negative x. So I think we've done enough of those with chain rule to be able to understand where that negative comes from. All right, now, according to the formula, this integral turns into this expression. So I'm going to take u, which is 2x, that's u, and I'm going to multiply times v. Now I had a negative there, so I'm going to pop that out in the front. Negative 2x e to the negative x minus the integral, and then we're going to do v again, so do v, which is negative e to the negative x, times du is 2 dx. So now I will take the 2 and the negative sign, bring it out, so it's going to turn into plus 2 integral of e to the negative x dx. And that integral I can handle. That's going to be pretty straightforward. So I'm going to have negative 2x e to the negative x, and then the antiderivative of this, we already did that, was negative e to the negative x. And then that's going to go ahead and join up with this 2. So we've got negative 2 e to the negative x, and then plus c. Getting a phone call. Okay, sorry about that. Where were we? Okay, so we have the antiderivative right here. So that's the right-hand side, and that should be what y is equal to. And that is it. We are done with that one. So now moving on to number 7. No, hold on. I was looking at the wrong thing. Okay, so number 7, we have xy prime equals 4y. So remember that y prime is really dy dx. And then we'll try and get all our y terms on one side and all our x terms on the other side. So I'm going to divide both sides by y, and then I'm going to multiply both sides by dx, and divide both sides by x. Alright, so we really have something that looks like this. 1 over y dy equals 4 times 1 over x dx, something like that. And now what we can do is integrate both sides, and then on the left side, notice that we have natural log absolute value of y. Okay, that is the antiderivative of 1 over y. On the right side, we have that constant 4, and then the antiderivative of 1 over x is natural log of the absolute value of x, and then we have plus some constant. Now you can call it c or c1, whatever you want. I'm just going to call it c this time. And now what we want to do is try and solve for y. So using the property of exponents, that if x equals y, if we have an equality, then e raised to the x equals e raised to the y. So, you know, if we look at this left side as being like an expression x and it's equal to some expression y, then I can essentially just take e and raise it to both sides like this, and that this equation is equivalent. Like that. Okay, so the reason I do that is because e to the natural log of y the e and the natural log are going to kill each other off, and you're just going to get y. And then on the right-hand side, I'm going to do a couple of things. I'm going to take this 4 and use property of logs to bring it up as an exponent. So I have e to the natural log of x to the 4th. Don't need the absolute value because I'm raising it to the 4th power. And then plus c. And then that becomes y equals e to the natural log of x to the 4th times e to the c. And that's just, again, another property of exponents. You know, if you have x to the n times m, that's equal to x to the n times x to the m. So I'm just using that property right there. And you know what, let me change this c to c sub 1. There we go, like that. And then the reason I'm doing that is just because at the end here, e raised to some constant is still some constant. So I'm going to call that c. And then again, the e to the natural log of x to the 4th, the e and the natural log are going to kill each other off. So you're just going to get the x to the 4th, and you're going to have a constant. So c times x to the 4th should be my my function. All right, so this is it right here. Okay, let's move on to number 8. Okay, number 8, you've got dy dx equals, oh no, plus 2xy equals 0. All right, so let's try and get everything going here. We've got dy plus 2xy dx. I'm multiplying everything by dx. Oh, sorry, 0 over here. And then let's try and get all of our x terms. So let's divide everything by y. So if I divide this first term by y, I'm going to get 1 over y dy plus 2x dx equals 0. And let's go ahead and just move this to the other side over here, so it's going to become negative. So what I'm going to do is I'm going to just cheat a little bit, like that. Okay, so now we've got this, and now we can integrate. All right, so we've got natural log of y again. And then over here, we've got just negative x squared plus some constant, like that. And we'll do the e on both sides again. I'll do that up here. E to the natural log of y equals e to the negative x squared plus c. And let's do that c1 again. You don't have to do that, okay? It's just totally up to you there. Okay, so now this splits up again, e to the negative x squared, and then times e to the c1, like that. And I guess we could leave it. We could have left it, but this is a constant, right? So I'm just going to kind of clean this up and write it as constant times e to the negative x squared. Here we go. So again, let's not lose sight of things. What we're saying is that this equation right here, this equation, is a solution to that differential equation. All right, number 9. dy dx equals y cubed over x squared. All right, so I'm going to get the y's on one side, so I'm dividing both sides by y cubed. And I'm also going to multiply both sides by dx. And that x squared in the denominator here is really just going to turn out to be that. All right, integrate again. Let me just clarify that this is the same as y to the negative 3 dy equals integral x to the negative 2 dx. And so we'll use a little power rule here. So let's see, we're going to have negative 1/2 y to the negative 2. That's the antiderivative of y to the negative 3. So again, just as a reminder, that the antiderivative of x to a power is that, so long as n is not negative 1. In the case that it's negative 1, it's the natural log. So that's just reviewing some stuff there from Cal 2. All right, so now over here we got negative x to the negative 1 and then plus some constant. So then we can clean this up, or let me see here. Let's just multiply everything by negative 2. So negative 2 here, negative 2 here. So distribute, 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 or not distribute, that's just multiplication. So we get y to the negative 2, and then we get, let's see, negative 2 hits that first one, so it becomes positive 2x to the negative 1. And then when I do negative 2 times a constant, I still get a constant. So why don't we call that one C1, and we'll just call this one C. And this is it. We have an equation, okay? This is the same as like y, 1 over y squared equals 2 over x plus some constant. So we're just looking for an equation. We've got it. A relationship between x and y. Number 10. dy dx equals y plus 1 over x. And same story. Let's get our y's on one side. Let's get our x's on the other. So just doing some division and multiplication to get things moved around. And then at this point we integrate again. Okay, on the left side we have a little bit of a substitution, but I think it can be done mentally. This is just going to be natural log of y plus 1. And then equals, we've seen this before, natural log of x plus some constant. Now we're going to do e on both sides, so let me just let's just cheat a little bit. E to that, and then that's going to give me just y plus 1 over here. On the right hand side I've got e to the natural log of x, and then times e to the c. And I'll do my c1 again, and then I'll switch it to c in a second. And then at this point we have y plus 1 equals x, and then times c. This is just a constant here. And we could say y is equal to c times x, some constant, times x minus 1. That would work. Okay, that's it for that. All right, number 11, we've got, be careful here, this is dx dy, not dy dx, equals x squared y squared over 1 plus x. All right, so we're going to need to try and get our y terms on one side, so I'm going to divide both sides by x squared and multiply both sides by 1 plus x. Like that. Leave my dx on the left. Divide both sides, multiply both sides by dy, which gives me y squared was the only thing left on the right. Something like that. And then we're going to integrate. Okay, on the left-hand side, go ahead and split this up into two fractions. So do 1 over this, and then plus x over this. So that's going to be x to the negative 2, and then plus x to the negative 1. Or actually, I'll write that as 1 over x because the antiderivative of that's just natural log. So, and then over here, we'll just integrate this. No problems there. So the antiderivative of x to the negative 2 is negative x to the negative 1, and then the antiderivative of 1 over x is natural log of x. Then we have some constant, and that equals 1/3 y cubed. And I could then multiply both sides by 3. It doesn't matter, but that is an equation that relates the two. Hold on a second. Just check on something here. I'm trying to get this to match the back of the book so that there's no confusion on your end. Yeah, I see what they do. I guess you could do that. All right, they multiply everything by 3x, okay? And they do that because this first term here, I'm going to erase it. That's really 1 over x. So it's like they're almost clearing the fractions multiplied by a common denominator. So if you multiply this by 3x, you should get -3, and then minus 3x natural log x plus some constant still, because, you know, 3 times a constant, still a constant. So I'll call that C1, but when you multiply it times 3, it's just some new constant times x. And then equals, when you multiply by 3 here, you get 3x, sorry, you get xy cubed. Okay, so that's what the book does, but we were actually okay at this line. All right, number 12. Okay, so number 12, dx dy again equals 1 plus 2y squared over y sine x. Okay, let's get all our x terms on the left side, so multiply both sides by sine x dx equals, and then multiply both sides by dy, so you get 1 plus 2y squared over y, and then we have dy. Let's split up the right hand side, so we got 1 over y plus 2y, so that's again doing this and this separately, and then dy. And I'll put that in parentheses, and I will integrate like this. The antiderivative of sine is negative cosine plus some constant, and then on the right hand side we get natural log absolute value y plus y squared. Okay, this looks good. All right, let's move on. 13. What is going on? Sorry, I've got another computer over here. It's acting funny. Okay. 13. We've got dy dx equals e to the 3x plus 2y, like that. All right. There we go. Got my other computer to stop acting funny. Should have paused it for you. Sorry. I'm just really trying to figure out what's going on. All right, got it. All right, so now we've got to get our y's and x's together on separate sides. So I'm going to use property of exponents again to rewrite the right-hand side like this. Okay, and that will allow me now to divide both sides by e to the 2y. Divide here, and that'll join it up with this dy on the left. And I'm going to multiply both sides by dx. So we should get e to the negative 2y dy. That's the same as dividing by e to the 2y. And then on the right-hand side, e to the 3x dx. And I think we're integration time. So we should get negative 1/2 e to the negative 2y is the antiderivative of this guy. You might have to do a little substitution. Okay, I'll do this one just for this one. All right, I really am anticipating you know how to do this, but just to be sure. So I make a basic u substitution. U is negative 2y. The derivative of u is going to be negative 2 dy. And then what I do is I try and rewrite this integral. So I need to replace dy. So what I do is I come back over to this equation. I solve for dy. So I put negative 1/2 du equals dy. So dividing both sides by negative 2. And then I'm going to rewrite this right here using this u. So this integral becomes e to the u times dy, which is negative 1/2 du. I pull the negative 1/2 out of the integral, and then I'm just integrating e to the u du, which is itself negative 1/2 e to the u plus some constant. But then u was negative 2y, so I replace it, and that is exactly what I have here. So that's our little basic u substitution. On the right hand side we get pretty much the same principle, and that's the antiderivative, and then plus some constant like that. So there we are. That's good enough. We could clear the fractions, but that is an equation relating x and y together, so I'm just going to box it up. I think in the book in the back they looks like they multiply both sides by 6 or something like that. Okay, 14. I better go to a new page. E to the x y dy dx equals e to the negative y plus e to the negative 2x minus y. That looks pretty messy. All right, let's see if we can't get all of our things together here. First thing I'm going to do is just multiply both sides by dx. So this term gets hit with the dx, and then the next term gets hit with the dx. Okay, next thing I'm going to do, this is going to look kind of weird, but just going to rewrite this. And just keep in mind that this is 1 over e to the y here. And keep in mind that this really is e to the negative 2x times e to the negative y dx. But I'm going to take this and drop it down. So that's going to be e to the y on the bottom like that. So I'm going to multiply everything, both sides of the equation, by e to the y. So I'm going to have e to the x, e to the y, y dy. And then when I multiply this by e to the y, I just get 1 dx. When I multiply this by e to the y goes away, and I just get e to the negative 2x dx. So I almost have all my x terms on the right and all my y terms on the left. I can just divide through by e to the x here. So why don't I do that? Divide this by e to the x, and then divide this by e to the x. And then it'll go away on the left. So now what we have is e to the y. I'm going to put the y in front. Y e to the y dy. And then we have e to the negative x dx plus, and then the next one we take negative 2x and we subtract x, that's e to the negative 3x dx. Now these both have dx in them, so what I'm going to do is factor the dx out and just go like this. Okay, and that should be it. We should be at a good point here where we can integrate both sides. And let me do the right side first because it's the easier one. Negative e to the negative x is the antiderivative there. And then minus 1/3 e to the negative 3x is the antiderivative of this one. Again, just using a little basic u substitution. then plus some constant like that. Now, the left-hand side, that is going to require integration by parts. So I'll do that over here. I'm going to say u is y, dv is e to the, what was it, positive y, dy. And then du has to be then dy. The derivative of y with respect to y is just dy. And then u equals antiderivative of e to the y is e to the y. So we're going to do that formula uv minus integral v du, right? That's what we're using here. And so I'm going to say that the left-hand side is u times v, so y e to the y, minus the integral of this right here, these two. So e to the y dy. And the antiderivative of e to the y is just itself. So we've got that, and then equals negative e to the negative x minus 1/3 e to the negative 3x plus c. Okay, so what number was this? 14. Let me just check this. So y e to the y minus e to the y, and then e to the x 1/3. Yep, okay, we're good. They moved some things around, but that's like they moved all these two terms to the left, but it's the same thing. All right, number 15. All right, I have 4y plus yx squared dy minus 2x plus xy squared dx equals 0. All right, so I'm going to have to almost expand all this out. So it's almost like I'm distributing the dy through everything here. And then I'm distributing the dx through also. Okay, so that gives us that. And now, let's see what we can do here. Why don't we move the dx terms? Well, you know what? I was going to move those to the right. We could do that, but I think what would be better, looking for any common factors now. Let's do it. So 4y dy plus y squared, or yx squared dy equals 2x dx minus xy squared dx. That should be a plus, sorry. Okay, so I just moved these guys to the right. Looks like I'm going to need to somehow get this y squared out of here, right? So I'm going to have to divide through, but I don't believe that's going to work. So let me just evaluate this for a second. Yeah, I think I'm going to have to do some factoring here. All right, let me go back. So the disadvantage to me not working these problems out first is that I'm going to maybe get hung up for a little bit, but at the same time I think that that's valuable for you to see that. So let me try something here. Just kind of thinking through different things here. Oh, okay. That's not that hard. Why didn't I see that to begin with? Okay, so look at these first two terms. I can factor out a y 4 dy plus x squared dy. Yeah, let me just take the dy out. How about that? Okay, so it's like I factored out a y and a dy at the same time. Then on the next one, I'm going to factor out a negative, and I'm going to factor out an x, and I'm left with a 2 plus y squared, and then I'm also factoring out a dx. So just check for yourself. If you multiply the y through and you multiply the dy through, you get back this expression. And then here, if you multiply through with the negative x and then the dx, you're going to get back those two right there. Okay, so now, at this point, what I'm going to be able to do, equals 0, sorry. What I'm going to be able to do is now move this whole expression over to the right-hand side. So let me do that, and I'm going to cheat again. I'm going to erase that. I'm going to change that to just equals. When it goes to the right-hand side, it becomes positive, so that works. And now check this out. We'll be able to divide through here by 4 plus x squared on both sides. And then I'm also going to be able to divide through both sides by 2 plus y squared. And some good things happen here. These are gone, and now we should just have everything on the left-hand side, y over 2 plus y squared. All right, that dy is, everything is in terms of y there. And on the right-hand side, we have x over 4 plus x squared, and everything there is in terms of x. So that worked out pretty nice. And now we can go ahead and integrate. So let me do one of these. I'll show the work on one of these. This one right here, when I do that, I'm going to make a basic u substitution. Use the denominator. And the reason I'm doing that is because I know that if I take derivative of that, I get 2x dx, which I almost have up top here. I'm off by a constant. So I'll just scale this. I'll do 1/2 du is equal to x dx. And therefore, this integral can be rewritten as 1 over u. That takes care of this part right here. And then the x dx can be rewritten with this 1/2 du. So I'll pull the 1/2 out and put the du back here. And so all we get here when we take the antiderivative is natural log of the absolute value of u plus some constant. But remember, u was this right there. So the right-hand side becomes 1/2 natural log absolute value of 4 plus x squared. Now, I do not need the 4 plus x squared to be in absolute value because 4 plus x squared is positive. I'll take care of that on the next line. Now, this antiderivative is very similar, and it comes out to be this right here. Okay, so now I'm going to say I'm done, but let me just see. Yeah, they go further. Okay, so they multiply both sides by 2. Okay, so we can do that. Kill that, kill that. And then they come in here and they do e here and e here. So when they do that, e on both sides, they get 2 plus y squared here. And then over here, remember this, this e, because of this plus right here, that can really be written as e to the c multiplied like that. And so why don't I call that c, c1 again? I'll go back and call it c1. Just remember that this is just some constant. So I have some constant times e and natural log here kill each other off, so you get 4 plus x squared. So that right there is a nice equation between x and y. Okay, going to be going here, number 16. All right, 1 plus x squared plus y squared plus x squared y squared dy equals y squared dx. All right, well, okay, so here's something we can do. We can split this up, 1 plus x squared dy. So that's basically like keeping these two grouped together but distributing the dy to them. And then on the next two, I'm going to factor out a y squared and put 1 plus x squared and then attach the dy to the end of that. So that's like these two. Pull out that y squared and then apply the dy to both. And then on the right hand side we have y squared dx. Now, oh, why don't we divide both sides by 1 plus x squared? How about that? That works out nice. Like that, and then at the same time, why don't we divide everything by y squared? And the y squareds are going to cancel, and the 1 plus x squareds are canceling. So we should get a nice expression here that's left here. We should have 1 over y squared dy plus, let's see, the y squared and y squared here cancel. We get 1 dy equals the right hand side, which is 1 over 1 plus x squared dx. And that can be rewritten as y to the negative 2 plus 1 dy equals 1 over 1 plus x squared. And remember, you cannot split those two up. And now we integrate. Okay, so the antiderivative here, we're going to get negative 1/3. Oops, negative 1 y to the negative 1 plus the antiderivative of 1 with respect to y is just y. And then equals over here, this should be something you are familiar with from Cal 2. That should be one of those special ones that you worked with a lot. This is arctangent of x, and then plus some constant. And so this is it. We have our equation. This is negative 1 over y plus y equals arctangent of x plus c. All right, that's number 16. Yeah, number 16. Yep. Moving to 17. 2y times x plus 1 dy equals x dx. All right, divide both sides by x plus 1. Okay, the antiderivative now. On the left, we just get y squared, so nothing tricky there. All right, so I think the problem with this one is just that this integration is just a little bit of work. We cannot split those up, so why don't we do a little long division? Why don't we do x here and then x plus 1 here? And then when we do this, to turn x into x, we multiply by 1, and then we put x plus 1 here, then we subtract. And when we go down here, this is going to be negative 1. So we have a remainder, so plus our remainder, negative 1 over our divisor, like that. So that's what this is. This is the integral of 1 minus 1 over x plus 1 dx. And that we can do just by basic antiderivatives. Antiderivative 1 with respect to x is x, minus, then this can be natural log of the absolute value of x plus 1, then plus some constant of integration. All right, that's it for number 17. Number 18. X squared y squared dy equals y plus 1 dx. All right. Looks like all we're doing here is we're just getting into some different sorts of integration. So I'm dividing both sides by y plus 1, dividing both sides by x squared. Ready to integrate. this is going to be negative x to the negative 1 when we take the antiderivative, because remember this is really x to the negative 2. But the left-hand side, I'm going to do, again, I can't split that up. So let me try a little bit of long division again of y squared here, y plus 1 here, and I have to multiply by y, then I get y squared plus y. I'm going to subtract, add down, I get negative y. So then multiply y by negative 1 to get that. So I put negative y and then minus 1 here. Add down, change the signs. So I get a 1 there as a remainder, so I put plus 1 over, or my remainder 1 over y plus 1. So on this left-hand side, we're integrating y minus 1 plus 1 over y plus 1 dy. So we'll have 1/2 y squared minus y plus natural log of y plus 1 equals, I'll put this as negative 1 over x plus c. So for 18, that is pretty nasty looking, but it is the relationship between x and y that we are looking for. All right, 19. Y natural log of x dy dx, or wait, sorry, dx dy equals the quantity y plus 1 over x squared. All right, well, a couple things are going to happen here. I'm going to divide both sides by y and multiply both sides by dy. You know what, let's do this. Let me clean this up. This on the right hand side, if we're squaring a fraction, we just square the top, square the bottom separately. Then I'll bring that x squared over by multiplying it on both sides. Okay, and then I'm going to divide both sides by y. And I'm going to still have that y plus 1 squared over here on the right. And then I'm going to multiply both sides by dy. So that should have just been algebra there. And then we have x squared natural log x dx equals, let's see, y plus 1, that quantity squared over y dy. Now on the right hand side, this we can expand the numerator out to be that, and then over y dy. And what's good about that is that I can split that up into 3 different terms. So this is going to be y plus 2 plus 1 over y dy. I can integrate each of those pretty easily. But on this one, to integrate that, oops, I never put my, oh, I haven't integrated, never mind, sorry. Let me just bring this down. Then we'll throw our integration in here. Okay. All right, so we're going to integrate this, we're going to integrate this. So the right-hand side should be no problem. And I need to figure out how to integrate this. So again, I'm going to do integration by parts here. And my choice of u is actually going to be the natural log function. Even though the derivative of x squared is easy, if I put the x squared dx here as my dv, my v looks like a u, then the antiderivative of that is 1/3 x cubed. All right, but on du, the derivative of natural log of x is 1 over x dx. So that's good because when I put these together in the new integral, those x's are just going to cancel. You'll have a 1/3 x squared. So trusting that you've kind of had enough experience with the integration by parts, here's the formula: u times v minus integral, and then like I said, I'm multiplying these two together. So that's going to give me a 1/3 x squared dx. Then equals, on the other side, antiderivative is 1/2 y squared plus 2y plus natural log of y. So that's my right side, just antiderivative there. And this antiderivative is pretty clear. So we're going to have 1/3 x cubed natural log x minus 1/9 x cubed plus some constant equals this side. So just be careful here that 1/3 comes out, but then the antiderivative of this is going to have another 1/3, so it becomes the 1/9. Let me just double check this result. Let's see. Looks good. Okay. Number 20. I think I'm getting like to the almost to the halfway point of this assignment. Goodness. Number 20. Oh wow. Okay, so I have 2y plus 3 all over 4x plus 5, but all of this squared. So same thing, I'm just going to apply the square to both the top and bottom, and then I'm going to try and get my dx to the other side, so I multiply by it, which means I'm going to have to bring my y stuff to the other side. So when I do just some algebra here, I should get 1 over 2y plus 3 squared dy equals 1 over 4x plus 5 squared dx. And I think I'm ready to integrate. And even though these look bad, they're not that bad. I'm going to just do this one over here. Okay, so I'm just going to make a basic u substitution. U is 4x plus 5. Du is 4 dx. So in my problem, I just have 1 dx. So I could just scale this. 1/4 du is dx. And now I just rewrite this integral. So the integral is 1 over u squared. That's the 1 over 4x plus 5 squared. And then 1 dx, right here, this gets replaced with 1/4, which I'll bring out, 1/4 du. And then this inside here is really just u to the negative 2, so the antiderivative of that is negative 1 u to the negative 1 plus a constant, which is really just negative 1 over 4u, like that. And if we want, we could write that as negative 1 over 4 times 4x plus 5. Okay. You know what? I'm actually going to write that as negative 1/4 times 1 over 4x plus 5. I'll just write it like that. Okay. All right, so when we integrate the right-hand side, I get negative 1/4 times 1 over 4x plus 5 plus some constant. And then when I do the left-hand side, I would do the same thing, just a basic u substitution with that 2y plus 3 being my substitution. And we would get negative 1/2 times 1 over 2y plus 3. All right. And I'm pretty sure they're not going to leave it like that. I guess they kind of do. They multiply both sides by negative 4. So if I multiply this side by negative 4, that goes away. If I multiply this side by negative 4, that's going to just turn into a 2 here. So that's what they have. And then, of course, you know, negative 4 times the constant, still a constant. So, all right, not too bad. Okay, working on number 21 now. Starting to use some different variables here. D capital S over D R equals K times S. Now K here is assumed to be a constant. So what we need to do is get our dr and our ds on separate sides. So I will divide through by ks, and that'll give me 1 over ks ds equals, and then I multiply both sides by dr, I get dr. Then I integrate. Okay, so the constant comes out, and the antiderivative of s is just natural log of s. And then we'll say plus some constant, and then equals the antiderivative of 1 dr, which is just r. So that's that. Now, I can do a little bit more if I want to try and clean this up, I guess I should say. Let me multiply both sides by k. I'm trying to get this to match the back of the book again. That is a sufficient answer, but let me try and match this up. So natural log of s, multiplying both sides by k, plus, and let's change this c to c1, and when I multiply that by k, I get a new constant, which I'll call c. Then equals k times r. So I multiply both sides of the equation by k. Now I will subtract c on both sides, and then I'm going to do e like this. We're familiar with that. We've seen this a few times. And you know what? Because I know we're going, let's call this c c2 instead. Now the left side of this is going to become s, because the e and the natural log kill each other off. And on the right hand side, we're going to get e to the k times r times e to the negative cr, so c2, sorry. And remember, this right here is still just a constant, so I'm going to call that capital C. I mean, sorry, lowercase c. C, and then e to the k r. Okay, so that's a relationship between s and r, and it includes the constant k. All right, moving along. 22 dq over dt equals k times q minus 70. Let's go ahead and multiply both sides by dt, and let's divide both sides by k times q minus 70. So that's what I get on the left. On the right hand side I have, now I left, you know what, let's leave the k over there. K dt. So I multiply both sides by dt, divide both sides by q minus 70. And now I should be able to integrate. So the right hand side is just going to be kt plus some constant. And the left hand side, I better call that constant 1. And the left hand side is natural log of q minus 70. And then I think we'll do e on both sides. I mean, we're good at this point, but let's do e here. So we get just q minus 70 on the left equals e to the kt times e to the c1. And remember, this right here is just some constant. So let's just throw it in front as a constant and get rid of it in the back. And then we can add 70 to both sides, I guess, if we wanted to, or just leave it just like that. Doesn't matter. Not so bad. dp dt equals p minus p squared. All right, so let's go ahead and divide by p minus p squared. And let's multiply both sides by dt. And now we get to integrate. Now the right hand side is t plus a constant, no problems. But the left hand side is the integral of 1 over p minus p squared, and that is not a familiar formula or anything. So I'm going to factor out a p on the bottom. And then you should recognize 1 over p times p, 1 minus p, as something we would do with partial fraction decomposition. So what I need to do is see if I can't rewrite this as some constant over p plus some other constant over 1 minus p. So we go through the process of now clearing fractions. So I multiply both sides by p times 1 minus p. I get 1 equals a times p minus 1 plus b times p, or bp. And then you have a couple of choices on how to do this. I'm just going to do what I refer to back in my pre-calc class and in my Cal 2 classes, just like the shortcut. I'm going to let p be equal to 0, and that should allow me to solve for a. So if I let p be 0, I rewrite the equation. Get a times p minus 0, and then plus b times 0. See, that kills off b. And all I get is 1 is equal to a p, right? Sorry, no, I totally jacked that up. This right here is 0 minus 1. I apologize. Then that's negative 1. So if we solve for a, we get a is negative 1. So I know up here that that's negative 1. And now to solve for b, I do something similar, but this time I let p be equal to 1, and that should kill off this one. So I rewrite the equation. A times 1 minus 1, that's going to be 0, plus b times 1. This is gone, and you just get b as 1. So up here, b is 1. So when I go back to this integral, after my partial fractions, this becomes negative 1 over p plus 1 over 1 minus p dp, and I had already integrated the other side, so t plus c. Now, this is just we're going to get some natural logs here. So minus natural log p plus, actually it's going to be minus. There's a little bit of chain rule there. Be careful. Minus p like that. And then we already took care of plus the constant on the other side, so no worries about that. And let's factor out a negative. And once we do that, we get natural log of p minus natural log of 1 minus p, and then equals t, and then plus c. The reason I did that is, oops, that's a plus, is to use property of logs, that I can put those two logs together as p times 1 minus p like that, and then a negative out front, and it equals t plus c. And then that's just negative natural log of p minus p squared equals t plus c. And oh man, okay, why don't I do this? Natural log of p minus p squared equals negative t. So I'm multiplying both sides by negative 1. But then when I say minus, it'll be minus c, but it doesn't matter. It's subtracting a constant, the same as adding a negative constant, so that really doesn't have an impact. And then finally do e on both sides. So e, and let me see, we're going to get p minus p minus p squared on the left, because the e natural log cancel out. Then I'm going to get e to the negative t times e to the c. We've done that a few times, and then this is just a constant. But I didn't change it, so I'm just gonna call it like this: p minus p squared equals that constant, which I'm going to call c1, and then e to the negative t. All right, let me check that. Where is this one? Did they even go further, and did they solve? Yeah, they solve for p. Okay. Well, I don't think I even want to solve for p. It's okay, because this is correct. Yeah, let's just leave it. I think we've done the crux of the problem here. All right, 23. We can go to 24 now. Oops. Yeah, 24. dn over dt plus n equals n t e to the t plus 2? Yeah, let me just double check I've got that. So we've got to get our dn and dt separated here. Why don't we start by just dividing everything by n? Okay, so I'm going to have 1 over n dn dt plus 1 equals t e to the t plus 2. Okay, so that's that. Now let's multiply both. Well, let's move that 1 over. So I'm going to subtract 1 on both sides. All right, now let's multiply both sides by dt. So I'm going to have 1 over n dn is on the left equals t e to the t plus 2 minus 1 and then dt. And we should be at a point where we can integrate. So we have natural log of n, plus a constant, let's do it here, equals, and then over here, well, this is going to be integration by parts. So let's try that little table over here. I'm going t, this is going to be dt, I'm going to go a little faster here, e to the t plus 2, and the antiderivative of that is e to the t plus 2. So that integral should turn into the integral of t e to the t plus 2. That would be like the u times v. Oh, I'm sorry. No integral yet. Minus integral of v du, which would be these two multiplied, which is just e to the t plus 2 dt. And then do not forget we had minus 1. We have to take the antiderivative. So minus t there. And then plus a constant, but I've already got that. Just remember that this right here is inside the integral. This is a separate piece. It's not inside the integral. So now we have equals t e to the t plus 2 minus itself e to the t plus 2 and then minus t. And then equals this side natural log of n plus c. All right, I'm happy with that because it gives us a relationship. Yeah, and they look like they're happy with that too. So I'm going to leave it just like that. And let's see how my battery's doing here. Okay, it's good. 24, 25 now. All right, some trig functions. Secant squared of x dy plus cosecant y dx equals 0. Well, we could just integrate right now because, oh no, sorry, they're not separated. Oops. All right, let's separate. So I'm going to move the cosecant to the other side and make it negative. There we go. And then divide through by cosecant y and divide both sides by secant squared y. So I will get, I'm going to go ahead and divide both sides by this. I'm going to bring the negative. So negative 1 over cosecant y dy, and then divide both sides by secant squared. So 1 over secant squared x dx. And remember, cosecant, right, is the reciprocal of sine. So 1 over cosecant is just sine. So this is just minus sine y dy equals, and then over here, secant is the reciprocal of cosine. So this is really just 1 over cosine x, that quantity squared. So we flip it, and so the right-hand side becomes cosine squared x dx. And now we can integrate. And I'll put my integral sign right there because the negative can go out front. And, well, you know, yeah, it doesn't matter. The antiderivative of sine of y is going to be negative cosine of y. So this is just going to be cosine y plus a constant. And then cosine squared x we have to integrate. And you have a couple of options on that. But the option we probably use in like a Cal 2 class is to rewrite that as 1/2, then 1 plus cosine 2x. So we're using the power reducing formula, or sometimes it's referred to in the books as half angle identity. So this is really going to become integral, the 1/2 comes out, and we're integrating 1 plus cosine 2x dx. And so now we have antiderivative of 1, which is just going to be x. We have a 1/2 out here. And then the antiderivative of cosine of 2x is going to be 1/2 sine 2x. There's a little chain rule involved there you have to account for. You've got to account for that 2 in there, which is where this 1/2 comes from. So you can do that with just a basic U substitution. But again, I do believe that that is a Cal 2 skill that you should all be familiar with. And cosine y plus c. All right. That's good enough, I think. Yeah, doesn't look like they multiply by 4. Yeah, it's good enough. All right. What was that, number 25? Okay, I'm doing kind of 5 at a time here. Okay, 26. Sine 3x dx plus 2y cosine 3x cosine cubed 3x, sorry, cosine cubed 3x dy equals 0. All right. So let me move this whole expression over to the right side, which is going to make it equals negative. And then I'm going to divide both sides by cosine cubed 3x. So we have sine 3x over cosine cubed 3x dx equals negative 2y dy. And we're ready for integration at this point. So on the right hand side, no big deal. But on the left hand side, we need a basic U sub. My basic U sub is U is going to be cosine 3x. du is negative sine of 3x, and then chain rule says that times 3. So I have negative 3 sine 3x is du, and that's almost what I have up top here. So what I'm going to do is just scale this, multiply by negative 1/3, like that, and then I rewrite the integral. I'm going to have 1 over u cubed, 1 over u cubed, and then I have that negative 1/3 du, like that. And then the inside there is really u to the negative 3. So when I take the antiderivative of negative 1/2, u to the negative 2 plus a constant. Don't forget the negative 1/3 out front. So it looks like we're going to have 1/6 u, which is cosine of 3x, but all of that to the negative 2 equals that. Okay, now what else do we need to deal with here? They're probably going to rewrite cosine to the negative 2 as 1 over cosine squared, and that's probably going to be written as secant squared, my guess here, number 26. Let me see here. Yeah, that's what they do. Okay, so they just rewrite this as 1/6. And again, this is really 1 over cosine squared of 3x, so that just becomes secant squared 3x equals negative y squared plus c. All right. Looks fine to me. 27. E to the y sine 2x dx plus cosine of x times e to the 2y minus y dy equals 0. So again, I'm going to move this whole thing over to the right side, so cheating here, make that negative, and then I'm going to divide both sides by this, no, sorry, I'm going to divide both sides by cosine, and I'm going to divide both sides by e to the y. So I'm going to have here sine 2x over cosine x. Let's go ahead and bring the negative over also. And then dx equals, and on the right hand side, e to the 2y minus y over e to the y dy. Alright, ready for integration. So integrate here, integrate here. Let's grab that negative and just take it out. There we go. Now, on the left-hand side, there's a little identity from pre-cal. Sine of 2x is really 2 sine x cosine x. And that's really nice because my cosines cancel. So now I just need to find the antiderivative of 2 sine x. And the antiderivative of sine is negative cosine, and the 2 will come for the ride. So we should just get 2 cosine x on the left-hand side, plus a constant. Then on the right-hand side, we've got a little more work to do. We'll split this up, do this over this, and this over this. So that should be, I'm just going to write it here, that should be e to the y, because e to the 2y over e to the y, you subtract the exponents. And then we're going to have y over e to the y, which I'm going to write like this, dy. So the first one here, the antiderivative is pretty clean. It's e to the y. And then the other one, I have minus, and now I need to take the antiderivative of this, and that's going to be a little bit of integration by parts. So I'm going to have y here, e to the negative y here, this is going to be negative e to the negative y here, this is going to be dy. So if I'm integrating, and I'm ignoring this minus sign here, that's already written down right here. So this integral, if I integrate just this piece here, I'm going to get these two multiplied, so negative y e to the negative y minus the integral of these two. And notice I had a negative there, so I'm just going to make this a plus, e to the negative y dy. And so I get negative y e to the negative y, and then when I take the antiderivative of e to the negative y, I get e to the negative y. I'm not going to worry about plus c because I already took care of that on the other side of the equation. So now I'm ready to go ahead and put this in here, but I have that minus sign, so it's going to distribute through, so everything's going to turn into a plus. Plus y e to the negative y plus e to the negative y, and that's it. Let me just take a look at this solution here. E to the y plus e to the negative plus y e to the negative y plus. Yep, good to go. 28. Secant x dy equals x cotangent y dx. Okay, so let's divide both sides by cotangent, and let's divide both sides by secant. So when I divide by cotangent on the left-hand side, cotangent y, and divide both sides by secant x, that's what we get. Now 1 over cotangent is the same as tangent, so tangent y dy equals, and then over here this is really x. Secant on the bottom is the same as cosine on the top, because secant is 1 over cosine. So that is what I'm looking at here. Now we need to integrate, and to integrate the left-hand side, there's actually a formula. You can probably find it in your calculus book, but I'm going to try and just do this by just reminding you this is sine of y over cosine of y dy, that's tangent. Then I make a basic u substitution and let u be this. So if u is cosine y, du is negative sine y dy, which is what I have up there, except I'm off by a sign, so I'm going to change it to minus, change this to plus. Then I can rewrite that integral as negative du, and then 1 over u, like that. And the antiderivative of that is natural log of u, like that. And then I can bring the negative up as a power, negative 1. So I have natural log of u to the negative 1. But u is cosine, so this is cosine of y to the negative 1, not the arc cosine, but cosine to negative 1, so it's really 1 over cosine. So that's really, 1 over cosine is really secant. So at the end of the day, what I'm saying is that the left side here becomes natural log of secant y. Like I said, there's a formula for that, but that's the actual work for it. Now on the right-hand side, unfortunately, I've got to do integration by parts. And this is an ugly one. So let me just do this on a new page. I'm going to do integral x cosine x dx. I'm going to run an integration by parts here. So I'm going to have x here, dx here. I have cosine x. I hope you're okay with me writing it this way, and then sine x like this. So this integral becomes these two multiplied, x sine x, minus integral of, this one isn't that bad, integral sine x dx. So that's these two in the new integral. And the antiderivative of sine is negative cosine, so the negative is going to come out and make this here a plus, then x sine x, then plus a constant. So x sine x plus cosine x, that's not bad. So equals, x sine x plus cosine x plus some constant. And that should be it for that one. Okay, good. That was 28. Okay, in parentheses, e to the y plus 1 raised to the second power, and then e to the negative y dx, and then plus e to the x plus 1 raised to the third power times e to the negative x. Make sure I got all this right. dy equals 0. So again, moving this whole thing to the other side, it becomes equals and then a negative. And then I'll divide through, let's see, well, wow, okay, so everything's going to switch sides, basically, is what's going to happen here, except that to do that, all the exponents are going to change. So whatever was positive becomes negative, whatever is negative becomes positive. So let me do that. Hopefully you can follow that algebra. So the left side becomes e to the x over e to the x plus 1 cubed dx, and then the right hand side becomes e to the y over e to the y plus 1, all of that squared dy, and I had a negative sign right there, so I'm going to slap it there. Alright, so that's essentially dividing both sides by, you know, divide both sides by this, divide both sides by this, divide both sides by this, divide both sides by this. When you do all that, that's how it should work out. Now, integrate. Now on the left-hand side, I'm going to make a basic u substitution. U is equal to e to the x plus 1. The derivative of that is e to the x dx, which is exactly what we have right here. So that's just going to turn out to be an integral of 1 over u cubed du, which is really integral of u to the negative 3 du, which is negative 1/2 u to the negative 2, plus a constant. So that's going to be negative 1/2 u, which was which was e to the x plus 1 to the negative 2. All right, that's our antiderivative of the left, plus a constant, equals, now on this integral I have a negative sign outside. I'm just going to kind of, or right there, I'm just going to kind of put it here for now. And then the antiderivative of this one, you could do a basic u substitution just like we did on the other one. And basically it's going to be u is e to the y plus 1, du is e to the y dy. And then when you rewrite that integral without the negative I already pulled out, okay? It's going to be 1 over u squared du. And the antiderivative, that's u to the negative 2, integrating that, get negative u to the negative 1. So when that negative comes out, I go negative, and then u, which is e to the y plus 1, and then to the negative 1. So that is just positive e to the y plus 1 to the negative 1 equals this here. And let's see what they have here. If they leave it with negative exponents, they do. They left it with negative exponents. So that's good. 30. Y over x dy dx equals 1 plus x squared raised to the negative 1/2 times 1 plus y squared raised to the positive 1/2. All right, so we've got to work this out here. I'm going to multiply both sides by x dx and then divide both sides by this. So when I do that, I'm going to have y over 1 plus y squared to the 1/2 dy equals, I multiply both sides by x, so I have an x on top, and then I'm going to rewrite that 1 plus x squared to negative 1/2. I'm just drop it to the bottom, and then I also multiply both sides by dx, so I've got that over there. So now I've got all my y's on one side, x's on the other, so integral, integral. And these integrals are almost identical, so I'm just going to do this one. Basic u sub, u is equal to 1 plus x squared. The derivative of that is 2x dx. I almost have 2x dx. I actually just have x dx, so I scale by 1/2. Now I rewrite the integral. 1/2 is going to come out, 1/2 du, and then I have 1 over, this is u right here, so this is square root of u, or u to the 1/2 if you'd like. Let's just do u to the 1/2. Not negative yet, I'm getting ahead of myself. And that's 1/2 integral of u to the negative 1/2 du. And the antiderivative of that is going to be 2u to the 1/2 and plus a constant. So this is really just u to the 1/2 plus a constant. So remember, u is this. So this integral on the right-hand side becomes 1 plus x squared to the 1/2 plus some constant. And then using the same property, the other side's going to do the same thing. 1 plus y squared to the 1/2, and then plus a constant, but I don't need to concern myself with that. So there it is, and we are done. All right, I have to admit I'm getting a little bit tired of doing this. 35. Wait, 35 did I? I wish I was on 35. I'm on 31. Okay, so 31, we've got y minus yx squared dy dx equals y plus 1 squared. All right. Okay, so look, on the left-hand side, let's pull a y out. Okay, and then let's multiply both sides by dx and divide by this, and then divide both sides by this. So the left side will have y, right side is y plus 1 squared, and then dy. And then equals the right-hand side, which I multiply both sides by dx, but then I divided by 1 over 1 minus x squared. So, got that. Now, I have to integrate, and I might start resorting to some formulas here if this looks like it's going to become kind of a nightmare of too much work, I think. So, this integration on the left, we should be able to do this with a basic u sub. Let me see, let me try this. U equals y plus 1. Let's try that. Then du equals just dy. And so when I rewrite that integral, I have to account for this y up here. So that y, what I do is I take this equation and solve for y. So y is equal to u minus 1. So u minus 1 on top, and on the bottom, what's nice is that this y plus 1 squared really just means u squared. And then dy becomes du. Okay, that's just from here. Now what's nice about this is I can split this up into u over u squared minus 1 over u squared du. And that's just going to become integral of 1 over u, and then this one is u to the negative 2. So now the antiderivative is what? Is natural log of u, and then antiderivative here we're going to have plus 1/3, nope, plus 1 u to the negative 1. I keep on doing derivatives. Okay, so let me just double check that. Take derivative of this, the negative 1 comes out, and then subtract 1. Okay, I'm good. So that's really 1 over u. And remember, u is y plus 1, so this is natural log of y plus 1 plus 1 over y plus 1. Okay, so that's my left side. Natural log y plus 1 plus 1 over y plus 1 plus some constant. All right, great. Now, on the right-hand side, this is a little bit ugly. I could do that with partial fractions. I could do that with trigonometric substitution, or I could do that using a formula. And I like the idea of using a formula, so please go reference a calculus textbook. Or should I work it out? And, okay, how about this? On this one, I'm going to work it out, but in the future, I don't think I'm going to want to go through all that. So my question to myself is, how do I want to do this one? Do I want to do partial fractions, or do I want to do trig sub? Let's do partial fractions. Okay, so this is obviously difference of squares on the bottom. Like that, like that. And so I need to rewrite that as a over 1 plus x and plus b over 1 minus x. Then I clear out the fractions, so I get a times 1 minus x, and then plus b times 1 plus x. And then I start letting x be certain things. So x is negative 1. That will kill off this second one. So if I let x be negative 1, we get 1 minus negative 1. That's going to be 2. So 1 equals 2a. So a is a half. So this a is a half up here. And then if I solve for b, I can let x be 1 this time. And that should kill off this one. So I should get 1 equals 2b. And so b is a half. So this b is a half. Life is good. So I'm really integrating here. Well, let me pull the 1/2 out because I have a 1/2 in both of those. So 1/2 integral, and I'm doing 1 over 1 plus x plus 1 over 1 minus x dx. And that should be equal to 1/2 and then natural log of 1 plus x. And be real careful on this one because you get a negative to come out because of that negative in front when you do your little u substitution. you have to account for that. So you should get that. And then that is just equal to 1/2. You can use property of logs here, that if you have subtraction between two logs, you can turn it into division inside of one log. Like that. And it would have been really easy to just use the formula that we had. But that takes you there. All right. And then I already have my plus c on this side. Natural log y plus 1 plus 1 over y plus 1. All right, double check this in the back here just to make sure. All right. Oh, they didn't even use the property of fractions, or property of logs there. That's okay. They just left it. They left it apart like this, but who cares? All right, 32. (32) 2 dy dx minus 1 over y equals 2x over y. My first instinct here is just multiply everything by y. That will clear out some fractions. Give us some nice terms that just have x in them. Why does this one seem a little too easy? Oh, sorry, I moved that 1 over. After I did that, I multiplied by dx. So something seems way too easy. Let me just make sure I wrote the problem down right. 32. 2 dy dx minus 1 over y plus 2. Okay. So antiderivative time. So we've got y squared equals x squared plus x plus a constant. All right, that's what it is. I don't know, it's kind of weird to have that problem just sticking in there. All right, 33. I'm sure they're going to make up for it now. All right, 33. dy dx equals xy plus 3x minus y minus 3 all over xy, yeah, they are making up for it now, minus 2x plus 4y minus 8. Okay, I kind of see what's going to happen here. We're going to have to do some factoring. All right, so let's see here. dy dx equals, what made me think of that is we've got 4 terms on the top and bottom. So I'm actually going to do this like this. I'm going to try and put those two together, xy minus y, and then I'm going to put plus 3x minus 3, just kind of reordering things. Then on the bottom, I'm going to do the same thing, xy plus 4y minus 2x minus 8. Let's just see what happens. I may have this going the wrong way, but let's try. I'm going to do grouping on these. So what I do is, on the first 2 terms in that numerator, I pull out a greatest common factor, which would be y. I'd be left with x minus 1. And then on the second 2 factors here, I pull out a common factor, which would be 3, and I'm left with x minus 1. And that's exactly what I was hoping to have. On the bottom, same thing. I pull out common factor here, y, and I get x plus 4. And I pull out a negative 2 out of these two, I get negative 2, and I get x plus 4 again. And that factors to be dy dx equals x plus 1, the common factor, times what's remaining, y plus 3, over, why does my computer keep going into some mode over here? Okay. And then on the bottom I have x plus 4, and then I have y minus 2. All right. Now we can work with that. Because what I'll do is I'm going to multiply both sides by y minus 2 and divide by y plus 3. So that means they'll go to the other side and they'll get flipped over. And then I'm going to bring my dx to the other side. So I should be in business at this point. So my left side is going to be y minus 2 over y plus 3 dy, and my right side is going to be x plus 1 over x plus 4 and then dx. All right, now I get to integrate. And I'm looking at some long division here. Y minus 2, y plus 3. So I multiply by 1, that gives me a y plus 3 here. I come through and change the signs, and that gives me a minus 5. So I get plus negative 5 over y plus 3. And then on this one, I do x plus 1, I divide it by x plus 4. It's 1, then I do x plus 4 here, and then subtract, change the sign, so I should get a negative 3 there, so plus negative 3 over x plus 4. Alright, so I get to now integrate. I'll just kind of cheat here. Let's go dy dx equals, right? That's the kind of where I am. I've done my long division. I can just rewrite those, and I'm integrating. So integrating those. Those integrals should be pretty straightforward. So antiderivative of 1 is y, and then minus, I have a 5 there, natural log of y plus 3. That takes care of that piece. Then equals, over here I've got natural log of, antiderivative of x, which is 1, which is x, and minus 3 natural log of x plus 4, and then plus c. All right, that looks pretty good. Yeah. Of course, yeah, they do a little more, but I'm okay with that. I'm satisfied. Just double checking it. Wait a minute. 5. Where did that 5 come from? Did I do it? Oh, man. I see my problem. Duh. This was minus 1, and I put plus 1 here. Damn it. Okay. All right. I'm going to fix it. This is minus 1. Let's see how that affects things. When I go here, this is minus 1. And when I add straight down, I get minus 5. And then this 3 becomes a 5. And then when I integrate, this 3 here becomes minus 5. Okay, now we match up. Okay, so I had a little technical error there, but everything else appears to be okay. All right. Moving on, 33, number 34. Man, that's the same sort of problem. I'm actually going to skip 34. That's the same sort of problem. So why don't I just tell you for 34 what you should get, because I don't really want to work through that whole exact thing. Okay, so that's 34 without the work. Let's go to 35. dy dx equals sine x times cosine 2y minus cosine squared y. All right, so this seems simple enough that you just divide both sides by cosine 2y minus cosine squared y dy, and then you just multiply both sides by dx, and we're here. So this seems pretty straightforward, but this integration might be a little bit messy. So I'm going to notice one thing here. This right here, I can use that half angle identity. Remember, that's 1/2 1 plus cosine 2y. And I'm wondering if that's going to help me. Yeah, hold on, pause, my daughter's in here. Okay, actually, I'm going to do something different here. I'm actually going to use a formula for this one. So it's basically the reverse. You can use a formula that says that is a double angle identity. Turns into 2 cosine squared y minus 1. Now, if you remember from pre-cal, there's actually 3 different formulas we could use there, but I'm going to use the cosine squared one because if I replace this, put that cosine squared y that was there. If I replace this first one with 2 cosine squared y minus 1, you'll see that these are the same, and so you're taking one of them, it was subtraction, and you are subtracting another one, so you're just going to get one of those cosines squareds. So this turns into 1 over cosine squared y minus 1 down there, yeah, like that, and then dy, and then equals the integral, the antiderivative of sine is negative cosine x plus c. So now this will be a little bit easier to work with because well, I'm trying to think if there's more than, yeah, we'd probably do it this way. This right here is negative sine squared y, that's just Pythagorean identity. And so what we have is 1 over sine squared y, which is going to be cosecant squared y, and we have a negative out front. So actually I'll leave the negative there, negative cosecant squared y dy. So all I'm using here is identities. And then now the antiderivative of negative cosecant squared y is cotangent y. So this is a known antiderivative, or we have a known, yeah, known antiderivative. This is cotangent y. So that's all that is on the left-hand side, and on the right-hand side, we just have this. So that is it. We are done. Oh, that's it. That's number 35. Okay, good. I'm going to start a new page here. 36. Secant y dy dx. I haven't mentioned this, but I'm using my tablet. And that thing that just happened, that happens. I cannot control that. I've tried to fix it, but I can't. My handwriting, I apologize if it looks sloppy, but I'm writing with a stylus on a glass screen, and it is, you know, I've been doing it for years, and it still is difficult to get used to. All right, so let me see. That's actually a plus now. Then equals sine of x minus y. Uh-oh. That looks like we're going to need some identity there. And then equals sine of x plus y. All right, so yeah, how about we start by using some identities here. We have an identity for this one. This is we call this the sum and difference formulas for sine, and I'm going to use it for both of these. So I'm going to rewrite this. Plus, this turns out to be sine x cosine y minus sine y cosine x, and then equals, this one is sine x cosine y plus sine y cosine x. So again, that's the sum difference formulas for sine. Now that should allow me to do some and let's over here, let's rewrite secant as 1 over cosine y. I might have to change that back later, but let's just do that. I think we get some canceling here. If I subtract this on both sides, it goes away. And then these two come together. I can add that, put it over here, and it's going to give me 2 of them. So that's actually pretty nice. 1 over cosine y dy dx. And that's all that's left on the left side, because I brought that other one over. I get 2 sine y cosine x's. And now I can start moving things around. So how about I divide both sides by sine y and multiply both sides by dx. So I'll have 1 over, oh, you know what? I'm going to divide by 2 sine y, and I can see why. You'll see why I'm doing that in a second. I have 2 sine y cosine y dy, and then on the right hand side I multiplied by dx, so all I should have is cosine x dx. Well, that's going to work out nice. I'm going to just use an identity here again, that the denominator is not 2x, is sine 2y, so this is a double angle identity. Dy equals cosine x dx. And then I can integrate, but on the other side, I'm going to rewrite this as cosecant of 2y, because 1 over that would be that. All right, so where am I at? I think for the cosecant, yeah, I will just use the formula. You could do that problem again. There's different ways, but that is a Cal 2 issue. So I'm going to go to my formula sheets, and again, this will depend on where you're looking for this, but the antiderivative of cosecant of something is natural log absolute value of cosecant of the argument 2y minus cotangent of the argument 2y. That's the antiderivative, but we would have to scale it by 1/2 because of like a basic u substitution. If we did a basic u substitution of 2y, we would have to pop a 1/2 out there. So that is the left side. And then of course the right side, very nice, sine x, and then plus a constant. So that is it. 38, that was 36, number 37. X root 1 minus y squared dx equals dy. So I have x dx, not bad, equals 1 over the square root of 1 minus y squared dy. And we're going to integrate. And to integrate this, did I put my integration symbols? Yeah, okay. To integrate that, the left side's easy, 1/2 x squared plus a constant. The right-hand side, you should recognize this. That was very special in Cal 2. This is arc sine of y, and I already took care of the plus a constant. So, yeah, I think we're good. I got my plus c over there. If we wanted to, we could take sine on both sides right now. Like that, and then have something like that. But that's not necessary. 38. That one was a little too straightforward. Okay, y 4 minus x squared to the half dy equals 4 plus y squared to the half dx. So going to divide through by this thing and divide through by this thing. So y over 4 plus y squared to the half dy equals, let's see, all I'm going to have there is 1 over, and then I'm going to do this a little different. I'm going to rewrite that instead of the 1/2, I'm going to put 4 minus x squared like that, dx. And for this one here, oh, let's integrate. So when we do this one here, this is going to be a basic u substitution. And I don't think I'm going to go through that basic u substitution. Yeah, well, yeah, I won't. But let's talk about the right-hand side. The right-hand side is that common formula again, and this is going to turn out to be arc sine of x over 2. All right, so that again should be a familiar formula, and we're coming from the property that that's our a squared. So that means a is 2 equals 2 in the formula. All right, so that's what we're going to get. And then on the left-hand side, this with that basic u substitution just turns out to be square root of 4 plus y squared. So you would just make a u substitution, let u be this, and then just work through it, and you should get the left-hand side. All right, that's it for 38. For 39. All right, e to the x plus e to the negative x dy dx equals y squared. All right, so if we divide both sides by y squared, multiply both sides by dx, and divide by the e to the x plus e to the negative x, then that's what we should get. And now we integrate. And the left-hand side, that's really y to the negative 2, so that'll become negative y to the negative 1 plus some constant equals, did I do a constant on the last one? I don't remember, did I? Oh yeah, I did, okay. And then over here, this is a little ugly looking, but we're going to do something kind of tricky. Whenever you see this e to the x plus e to the negative x, one of our common techniques is just multiply the top and bottom by e to the x. And so what you get is on top e to the x, and then over, when I do e to the x times e to the x, I get e to the 2x. Or if you'd like, I would prefer if I write that as e to the x squared, and then I have plus 1, like that, then dx. And I'm trying to integrate that. So what's good about that is if I just let u be equal to e to the x, then du is e to the x dx, and I have that right there. And so that integral becomes 1 over the integral of e to the x, which is u, so u squared plus 1, and du, exactly. So the antiderivative of that is arctangent of u, which is just arctangent of e to the x. And I already took care of the constant on the other side. So we should have on the right-hand side arctangent of, see, that's what I'm talking about, e to the x. Then the left-hand side is this. All right, that's it. 39, let's go to 40. Excited because I'm getting close to the end here. Well, at least the first 40 problems. I still have more to do in this section, but I'm just going to pick a few from the other ones. All right, so we have x plus root x, and then dy dx equals y plus root y. Let's just multiply both sides by dx. And divide both sides by the x root plus root x. And let's divide both sides by the y plus root y. So that's where we are. We need to integrate. So at this point on number 40, I think we're going to do something kind of crazy here. Let's just do this one. Both the integrals will work out the exact same way. I'm going to make a substitution, u is equal to root x, which doesn't seem very natural, but that's what I'm going to do. Du then is 1 over 2 root x dx. Now notice that if I take this and square both sides, I get u squared as x. So I'll be able to rewrite, let me put the integral that I'm working on right here. So I can rewrite this. I can replace this x with u squared plus, now root x, this one, this root x right here, can be replaced with u. That's this right here. And then dx can be replaced with, I take this equation, I multiply both sides by 2 root x. Okay, and remember, this root x is really u. So this is 2u du equals dx. So I'm going to put 2u du to replace my dx. And now, at this point, I can, let's see, factor a u out of the bottom, and then cancel the u's. And that means I have integral of 2 over u plus 1. Something doesn't seem right there. But let me just double check it. Yeah, that's right. Okay, du. And this is going to be 2 natural log of u plus 1 plus a constant. And that's 2 natural log of u, but u was actually root x, so plus 1 plus c. So the right-hand side becomes 2 natural log absolute value root x plus 1 plus c, and then the left-hand side would have gone exactly the same way, 2 natural log of root y plus 1, and I already took care of the plus c. So double checking here. Yeah, okay. Yeah, we could divide both sides by 2, and then we could do e on both sides. If we did e on both sides, that would be pretty nice, but let's just again leave it as is. And that's number 40. All right, going to be working the next few problems here, number 41. So now we start to shift gears just a little bit. We're given a differential equation, but this time we are given an initial condition, and we're asked to solve the differential equation subject to that initial condition. So let's just get this differential equation down first. All right. So here's the initial condition. Whatever function we find, y of 0 must be 0. So when we plug in x equals 0, we should get 0. And that will, instead of giving us a family of functions, we're actually going to nail it down to precisely one solution. All right, so same game as before. We're going to try and get all our x's and all our y's on separate sides. And so I will divide both sides by 1 plus cosine x. And I will also divide both sides by by e to the negative y plus 1. And then before I integrate, I'm going to multiply e to the y on the top and bottom of this second one, and that's going to give me e to the y on top. And then when I multiply here to here, that just gives me a 1, and then here to here gives me e to the y. So I'm going to have 1 plus e to the y. So that's just some algebra that's going to allow me to integrate that. So here comes the integration step. On the left side, I'm going to set this to be my u, just a basic u substitution. The derivative of it is up here. We're off by a sign, so I'm going to have to put a negative. And then I'd have 1 over u after I make that substitution. So it's just going to be natural log of 1 plus cosine x plus some constant equals, now on the right hand side, I'm going to do a basic u substitution, let u be 1 plus e to the y. The derivative of it is exactly up here, and therefore my substitution yields the integral 1 over u du, which is just going to be natural log of whatever my substitution was, which in this case is 1 plus e to the y. All right, so this is it. This is my solution. Now I'm going to use the fact that when I plug in x equals 0, I need to have y equals 0. So let's just rewrite this now. Negative natural log 1 plus cosine, I'm plugging in 0 for x, plus some constant must equal natural log of 1 plus e to the y, but when I plug in x equals 0, I need y to be 0, so this is also going to be 0. And so what I get is negative natural log of 1 plus c must equal natural log of 2, and that's because e to the 0 is 1. And natural log of 1 is 0, so this is gone, and so you get that c must equal natural log of absolute value 2. You don't need the absolute value, but that is it. Now, hold on. Yeah, okay, so that's good. So now what we're saying is that our solution, given that initial condition, is negative natural log 1 plus cosine x plus natural log 2 equals natural log of 1 plus e to the y. So that when we take the derivative of this, we know that we differentiate that, we know that it will actually be a solution to this equation. But simultaneously, it satisfies the condition that y of 0 equals 0, so that when I plug 0 in here for x and for y, we get a true statement. So that is it. All right. Just a second here before I move on to the next one. Okay, 42. 1 plus x to the 4th dy plus x times 1 plus 4y squared dx must be equal to 0, and we have the condition that y of 1 equals 0. So that means when I plug in 1 for x, y should come out to be 0. Just keep that in mind for later. All right, working with this equation here, let's divide everything by 1 plus 4 to the x, and simultaneously 1 plus 4y squared. And what we would get is 1 over 1 plus 4y squared dy plus x over 1 plus x to the 4th, and then dx equals 0. And I'll do what I've done before. I'll just kind of cheat here and move one of these to the other side, so I'll make that a negative x up there. And now I go ahead and I integrate this. So I'm trying to figure out how I want to do this. Okay, so let's do something. This integral over here looks a lot like a formula that we have for arctan, but I'm going to factor a 4 out of the bottom first. So watch what happens here. If I factor a 4 out of the bottom, I'm going to get a 1/4 here, 1 over, and then if I'm factoring out a 4, then I'm going to need a 1/4 here plus y squared dy. And just check, if you take this 4 and distribute it through here and here, then you will get back the expression above. So that's just to make it look like 1 over a squared plus x squared for the formula, or for the formula for arctan. So I needed this to be an a squared and this right here to be just the variable squared. So, all right, that works there. Now on the other one, this one's a little trickier. I'm going to rewrite that x to the 4th as x squared squared. And if I do a real quick basic u substitution, also I'm going to take that negative sign, just put it on the outside of the integral. U is x squared, then du is 2x dx. I have x dx up top, so I just need to scale this so I get x dx. And now when I rewrite that integral, that 1/2 comes out, du is here, and then I have 1 over 1 plus u squared. And then the formula for that, I get 1/2 arctangent of u, but u in this problem is x squared. So the right side of this becomes negative, because I had a negative in front of the integral, 1/2 arctangent of x squared plus some constant. And then the left side of this becomes 1/4, and then using the formula for this, the integral of 1 over a squared plus x squared dx should be equal. I'm just going to the formula, I'm not doing anything else. 1 over a arctangent of x over a. So for us, in this problem, a is the number that's being squared here for us. That's going to be 1/2 squared. So a is 1/2 for us. So that's what's going to go into this formula right here and right there. And 1 over 1/2 is really 2. So I'm going to have here 2 arctangent. And then when I put the 1/2 right in there, x over 1/2 gives me 2x. And I already have my constant on the other side, so I'm good to go. Clear out some of this. And now remember, our initial condition was that y of 1 had to be equal to 0. So now what I'm going to do is I'm going to let y be 1. And let me just double check something here. 1/2 2x. Yeah. Okay, so now when x is 1, this right here is 1/2. So we get 1/2 arctangent of 2. That's when x is 1. You know, hold on, sorry. This should have been y, 2y. My apologies, my variable is y here. So that should be arctangent of 0. And then equals negative 1/2 arctangent of, and I'm plugging in 1 for x here, so arctangent of 1 plus c. Alright, so arctangent of 0 is saying, you know, like tangent of what angle, theta, equals 0. And that is going to be the angle 0. So this just gives us 0. So the whole left side is 0. And then this right here is saying, you know, tangent of what angle equals 1. And that happens at pi over 4. So we should be getting here 0 equals negative 1/2 times pi over 4. And that's plus c. So if I just move all this to the other side, I get pi. I'm just basically adding that to both sides. I should get that c is equal to, where did my 1/2? Oh, no, hold on. 1/2 pi over 4. Did they do a substitution here? No, we're at the same place. Okay, yeah. C must be pi over 8. We're good. They do slightly different things, which kind of throws my answers off from there, so I have to just double check some things. But C must be pi over 8 is what we get. So let me just write down our final result here. Our function that is a solution to that differential equation given the initial conditions is 1/2 arctangent of 2y equals negative 1/2 arctangent of x squared plus pi over 8. Was it plus? Yeah. All right, now just to be sure, I'm going to just check this real quick. What happens if we replace this with 0 and not theta, 0, and place this with 1? Then, of course, this was 0 equals, and then this right here was 1, so I get negative 1/2 times, not 1 is pi over 4, and then plus pi over 8. So these cancel. So yeah, that's true. All right, so we are good. Okay, get that. So here was our solution. I'm noticing that the problems, the answers in the back of the book are going to look a little bit different, but they're just doing different algebra. And so their C's look a little bit different, but the reason they do is because their original equation here looks a little different. Like they multiplied here by 2 here and 2 here, and killed off those fractions. And by doing that, that has an impact on this. So just trust your answers and work them through. And if you have any questions, let me know if you're getting something different than the back of the book. All right, next one. Where am I at? 43. Y dy equals 4x times y squared plus 1 to the 1/2 dx. We have the initial condition y of 0 is 1. All right, so let's get our x's and y's together here. So we're going to have y over y squared plus 1 to the 1/2 dy equals, it looks like just 4x dx. So the left side, when we integrate, we've got a basic u sub. Let u be equal to y squared plus 1. The derivative of that is 2y dy. Scale by 1/2 so that it matches up with what you have up there. You have y dy. So this integral becomes integral, I'll do it down here. Integral, the 1/2 comes out, du. Then we have 1 over u to the 1/2, which is the same as u to the negative 1/2. And so the antiderivative of that is 2u to the positive 1/2. So the left side becomes 2 times u, but u is y squared plus 1 to the 1/2, plus some constant, and then equals the antiderivative of the right side, which is 2x squared. And so now let's go and try and figure out what that c has to be. So to do that, I replace x with 0, so this becomes 0. And I replace y with 1, so we get equals 2. This is going to be 1 plus 1, that's 2 to the 1/2 plus c. And this is like 2 to the first power times 2 to the 1/2 power is 2 to the 3/2 power, plus c equals 0. So c must be negative 2 to the 3/2, just moving it over to the other side. All right, let's just check. What did they do? Root. Oh, did I? No, 2. Oh, I forgot the 1/2 here. Oops. This 1/2. Oops, I forgot it right there. 2. That's 1/2. That's good. That's going to kill off this 2. And kill off that 2. And then it's just going to be 2 to the 1/2. And then minus 2 to the 1/2. My fault. So just keep in mind there. We had that 1/2 here, and I never accounted for it right there. So that had a little bit of an impact. So our c is going to be negative 2 to the 1/2, which is the same as negative square root of 2. Okay. 44. dy dt plus ty equals y, and y of 1 is equal to 3. So let's just pay attention to the variables here. Here we're assuming y is a function of t, so when we plug in 1 for t, we should get 3 to come out for y. Just keep that in mind. So how about we divide everything by y first? So 1 over y dy dt plus t equals 1. And then how about moving the t to the other side? So that becomes 1 minus t. And then what about we multiply both sides by dt? All right. So now what we can do is just integrate each side. This looks like a pretty straightforward integration, natural log of y. plus some constant equals t minus 1/2 t squared. And now let's just plug things in. If t is 1, we get 1 minus 1/2. So that's just 1/2. Has to be equal to c plus natural log of 3. So moving things over, we get c is equal to 1/2 minus natural log of 3. We don't need the absolute value. So 44, double check here. Yeah, again, they did some things different, but I believe we are good here. So since I'm going to go to number 48, I'm going to stop this video and then come back. Whoa, okay. Working on next one here, 45. Make sure I'm recording. Okay. So 45, I've got dx dy this time equals 4 times x squared plus 1. So here's my condition. X of pi over 4 must be 1. So remember, this is the y value and this is the x value. So this looks like I'm going to divide both sides by x squared plus 1. Multiply both sides by dy. Integrate. You should recognize this left side as being arctangent of x plus some constant must equal 4y. And so now let's plug in for y. Let's plug in pi over 4. So that's just going to give us pi equals some constant plus plug in 1 for x. So arctangent of 1 is pi over 4. So c must be pi minus pi over 4, which is 3 pi over 4. So that's what we get for number 45. Okay, moving along. All right, working on number 46 here. I've written the problem down. And notice what x and y need to be to satisfy that initial condition. And so what I'm going to do first is get all my x's and y's separated here. So I'll divide by 1 over y squared. Divide by y squared minus 1 on both sides. Multiply both sides by dx. And then I will resort to a formula, just pointing out that this looks a lot like 1 over x squared minus a squared. So for both of these integrals, we have a as 1, and then resorting to the formula, the integral of this is going to be 1 over 2 times a natural log of the variable, which in this case is y, and then minus a over y plus a, then plus some constant, and then equals, we're going to have the same thing on the other side, 1 over 2 times a natural log of the variable x minus a over x plus a. All right, so at this point we can notice that this is 1/2, this is 1/2. We can multiply both sides by 2 and just be gone. And now let's just start plugging some things in. So if we plug in 2 for x and 2 for y, we get natural log of 1/3 plus c must equal natural log of 1/3 again. And if we subtract that natural log on both sides, it goes away and you just get c as 0. So if we just come back up here to this and we replace c with 0, this would be our solution to the differential equation that satisfies that initial condition. All right, 47. X squared y prime. I'm going to go ahead and write that as dy dx equals y minus xy. We have the condition that y of -1 must equal -1. All right, so kind of played this game already. I'm going to, on the right-hand side, I'm going to factor out that y so I can get one factor that doesn't have any y's in it. And then I will divide both sides by y. I will divide both sides by x squared, and I will multiply both sides by dx. And then I'm going to split this fraction up here into two fractions. So it becomes 1 over x squared minus 1 over x. And then I'll go ahead and integrate. So I've got natural log y here plus some constant equals negative 1 over x, that's the antiderivative of this, minus natural log of x. Okay, so I'm going to plug in negative 1 for y and for x, right? For x I'm plugging in negative 1, for y I'm plugging in negative 1. So I get natural log of negative 1, but the absolute value, so this is natural log of 1 plus c equals negative 1 over negative 1, that's just 1, and then minus natural log of absolute value of negative 1 is 1. So natural log of 1 is 0. Both of those are gone, and all you're left with is c is 1. That's pretty nice. Let's see here. Yeah. All right. 48. dy dx plus 2y equals 1. Y of 0 is 5 halves. Doesn't look too assuming there. Okay, so why don't we see what we can do here. Well, I guess we subtract 2y from both sides just to get one term over there, and then divide both sides by 1 minus 2y, and then multiply both sides by dx. And now we integrate. And when we integrate the left side, we've got to take care of some chain rule that happens. So we just let this whole bottom be u. When we do that, we should get this. So derivative of that, let me just do it in my head real quick. Yeah, that looks okay. And then the antiderivative of the right-hand side is just x, and then I'll do my constant over here this time. So now, at this point, we are going to plug in 0 for x and 5 halves for y. So negative 1/2 natural log of 1 minus 5 halves times 2 is just 5 equals x plus c. I forgot to replace x with 0, so that's 0. So it's just c here. And that doesn't look too bad. Negative 1/2. This is going to be natural log of the absolute value of negative 4, which is just 4. And what else can I do here? Equals c. I could bring this 1/2 power up like that and leave the negative out front, so I get negative, and then natural log of 4 to the half is the same as square root of 4, which is 2. And if you want even now, you can bring this negative 1 up here as an exponent. That would turn that into like a 2 to the negative 1, which would be 1/2. So natural log of 1/2 would be c. Okay. All right. That's it for 48.